There are moments in astronomy when the universe behaves so strangely that even the most seasoned researchers stop mid-sentence. Stare at the numbers glowing on the monitor and feel something close to disbelief stirring in their chest. That moment arrived when the latest batch of spectral and photometric data on 3I Atlas downloaded itself onto screens across observatories worldwide. The object had already earned attention simply for being the third confirmed interstellar visitor to sweep through our solar system, an emissary of unknown worlds, a shard from a star system that may have died before humanity even began. But this time, the surprise was not its origin or trajectory. It was the behavior hidden inside its light curve. Instead of the jagged staccato rhythm that comes from a comet tearing itself apart under the sun's rising heat, the brightness shift of 3I Atlas flowed like a breath, smooth, rhythmic. Measured, it was as if the object had found a way to resist the chaos that normally consumes such bodies. Astronomers ran calibration tests, rechecked exposure logs, and compared timestamps with collaborating observatories thousands of kilometers away. Every check returned the same quiet, unnerving answer. The object was not fragmenting. It was doing something else, something that did not fit into any established category. In dome after dome, under red safety lights and the slow hum of equipment, researchers watched the line on their screens settle into a curve that refused to match any known fragmentation signatures. The sun poured energy into the object, yet instead of cracking like a brittle stone, 3IATLAS seemed to stabilize. Telescopes captured jets, emerging at intervals so consistent they looked almost mechanical, though no one suggested machinery. Instead, they suggested physics we didn't yet understand. The jets weren't exploding outward in chaotic fountains. They were emerging like blades of controlled material, timed with the object's rotation cycle. The more images we acquired, the more obvious it became that the object was not losing mass in the destructive way comets do near perihelion. Instead of accelerating its spin into destabilization, the jets seemed to do the opposite, acting like tiny stabilizers, balancing the rotation instead of disrupting it. The spectral readings intensified the puzzle. Ratios of ices and minerals in its outer layers didn't align with anything typical for solar system comets. Some signatures hinted at hyper-cold formation environments, colder than anything near our own sun. Others suggested crystalline patterns etched across its surface by millions of years of exposure to cosmic radiation. And then came the thermal plateau, unexpected flattening of temperature, despite increasing intensity of solar radiation. Instruments from NASA, the European Southern Observatory, and independent astronomers all confirmed the effect. The temperature should have increased, but it didn't. It simply held, like an object shedding heat through a mechanism we had never observed. Theories multiplied across research groups. Some proposed supervolatile ices sublimating in a thin, uniform layer. Others suggested a crust that peeled away instead of shattering. A few wondered whether the object contained alternating layers of materials that released energy in steps rather than spikes. But none of these explanations accounted for everything: the coherence of its coma, the sideways jets, the rotational stabilization, the uniform secondary feature trailing behind it. What was clear even at this early stage was that we were not watching a comet breaking apart. We were watching something undergoing a transformation that obeyed rules we had not yet written. As more observatories turned their instruments toward the visitor, the narrative surrounding 3I Atlas began to shift from curiosity to something approaching reverence. For decades, astronomers have modeled comets as fragile structures, chaotic relics of planetary formation. Near the sun, they usually behave in predictable ways. Heat increases, ices sublimate, jets burst, rotation destabilizes. And eventually, the nucleus fragments into pieces that drift like debris boats on a gravitational tide. But 3I-ATLAS, forged somewhere far beyond our heliosphere, didn't follow the script. The coma, the glowing envelope of dust and gas around the nucleus, didn't bloom into chaotic patterns. Instead, It showed faint arcs, as though waves of material were moving outward in gentle pulses. No debris clouds, no rapidly shifting asymmetries, no signs of structural collapse. When imaging teams enhanced the data, subtle shell-like layers appeared wrapped around the object in patterns that seemed too orderly. Too layered, too steady to be the product of violent outgassing. Then there was the mysterious extension trailing behind it, not a fragment, not an ion tail, not a dust tail. It curved in a way that didn't align with solar radiation pressure or solar wind shaping. Some researchers argued that the feature might be a sheet of microparticles drifting in a resonant pattern with the object's rotation. Others suggested the possibility of extremely fine aerosol-like dust, released in an ultra-uniform wave rather than in explosive bursts. The object did not brighten or dim abruptly. Instead, its light behaved like a heartbeat-gentle dimming phases, followed by mild rebrightening. The pattern was so smooth that some astronomers, half-jokingly, wrote in their logs, "If it were alive, this is what the pulse would look like." But no one was claiming anything biological or artificial. It was simply an attempt to articulate how profoundly unlike traditional comet behavior the object's S-like curve appeared. The sideways jets deepened the puzzle. They fired almost perpendicular to the motion of traveling arrangement rarely seen in solar system comets. Normally, such jets destabilize a nucleus, contributing to chaotic rotational tumbling. But 3I Atlas responded in the opposite way. The jets reduced rotational noise, smoothing out the spin instead of throwing it into disorder. That alone suggested an internal structure unlike any we have cataloged. It might have layers of differing densities. It might have pockets of exotic ices arranged in patterns shaped during its formation near a distant star. It might contain cryogenic minerals capable of releasing energy in ultra-stable sequences. What made this object so scientifically precious was not the absence of fragmentation alone. It was the consistency, the repeated message it sent through every wavelength instrument. I do not behave the way comets from your system behave. And that message reshaped ongoing discussions about interstellar voyagers. Most of what we know about objects from other star systems rests on a sample size of 2, 1I Oumuamua and 2I Borisov. Oumuamua accelerated in a way we still debate, while Borisov behaved more like a standard comet with high fragmentation. 3I Atlas entered this shortlist and immediately broke expectations in a third. Entirely different direction, coherent behavior under solar heating. Scientists began exploring whether interstellar comets might not be a single category at all, but a diverse family shaped by environments across the galaxy. Some might form near stars that emit particular radiation patterns. Some might originate in systems with heavy cosmic ray bombardment, producing crystalline layers. Others might come from regions of extreme cryogenic temperatures, building ices unseen in our solar system. 3I ATLAs might be our first clear example of such diversity. As data accumulated, one thing was undeniable. This object wasn't teaching us about our solar system. It was teaching us about the galaxy. When astronomers speak about interstellar objects, there's always a trace of emotion beneath the calculations, because these entities are messengers from beyond our cosmic borders. They drift through space for millions or billions of years before we ever notice them, carrying chemical fingerprints of places our telescopes cannot yet reach. And 3I Atlas carried itself through our solar system with a dignity that felt almost ceremonial. Not breaking, not flaring, not collapsing. Instead, unfolding, evolving, displaying a kind of resilience that demanded we expand our ideas of what frozen bodies can do under stellar heating. As it curved around the sun and prepared to slip into the outer darkness again, scientists realized they were witnessing one of the rarest events in human history. A visitor from another star system performing a transformation that defied our models. Not violently, not chaotically, but elegantly. Its persistence raised new questions. What chemical bonds allow material to peel away in uniform sheets? Could ultrafine cryogenic dust create a smooth brightness cycle rather than jagged ones? Could the sideways jets be signatures of structural harmonics deep inside its nucleus, essentially a rotating system shedding mass in perfect rhythm? And if so, what processes could shape such a body in the first place? These questions didn't imply anything unnatural. They implied that the Milky Way holds a wider toolkit of physical phenomena than we have sampled. For years, we considered our solar system's comets as templates for how cometary objects behave everywhere. But each interstellar visitor has shattered that assumption. Oumuamua showed us that shapes and acceleration behaviors could be entirely unfamiliar. Borisov showed us that some interstellar bodies fragment explosively. 31ATL-AST now shows us that others may resist fragmentation. Altogether, perhaps because they were shaped in environments our instruments cannot yet imagine. As it continues outward on its hyperbolic escape path, astronomers know they might never see it again, yet its influence will remain. It forced us to abandon the comfort of assuming that comet behavior is universal. It challenged us to ask whether the galaxy contains ice is more fragile or more resilient than any found here. It reminded us that every object entering our system is carrying secrets from worlds we cannot visit. And it offered us a lesson in cosmic humility. The universe is not required to behave according to the categories we invent. It behaves according to its own physics that we are only beginning to glimpse. Long after 3IATLAs fades from our instruments, the questions it raised will continue shaping our understanding of interstellar matter. It will become a benchmark in future research, a reference point for phenomena we once considered impossible. And when the next interstellar traveler arrives, and it will, we will look at it with new eyes, trained by the quiet, measured resilience of this one. 31ATLAs entered our solar system not as a spectacle of destruction, but as a demonstration of endurance. Not as a problem, but as a conversation. Not as a comet breaking apart, but as a message from the galaxy, whispering truths we have not yet learned to decode. And its greatest legacy may be this: it reminded us that the universe still has surprises left. Surprises vast enough to challenge our theories, beautiful enough to expand our imagination, and silent enough to slip through our sky like a thought the cosmos forgot to finish.